Let's see, I just want to give a quick kind of a history lesson, I guess you'd say. And what I want to do is just talk a little bit about these rings that we've been studying recently, so the history of Z bracket root n. And we've been studying them the last couple of lectures in connection with multiplicative norms. And what we've seen, I mean, they provide sources for examples of sort of strange behavior that's not quite the same as what we think of or how we see in the integers, in rings of polynomials, and so on. For example, what was it, Z bracket root 5, that was our example of a non-UFD. We also had a place where we had irreducible but not prime, right? And that was in Z bracket square root of -3, right? So these rings right here are sources of examples of strange behavior, at least strange compared to what we're used to. And so what I want to do is just talk a little bit about where this came from, or whoever dreamed up such rings. So the existence of non-UFDs, right? We saw an example of a what was it, Z bracket square root of -3, right? It was not a, oh no, is it -5? -5, right? Yeah, -5, that's not a UFD. So the existence of non-UFDs, this came up, or this arose in connection with Fermat's last theorem. Now, you probably heard of this if you took number theory or something like that. Fermat's last theorem goes like this, so let's state it as a claim. So Fermat made this claim, if n is greater than 2, then the equation, let's say x to the n plus y to the n equals z to the n, has no integer solutions. All right, so of course when n equals 2, we've got the Pythagorean theorem that happens all over the place, right? There's lots and lots of integer solutions when n equals 2. And so Fermat makes this claim, if n is greater than 2, then there are no integer solutions. And of course there's this famous story. He writes in the margin of his notes, or in the margin of the book, hey, I've got a great proof of this, but the margin's too small to contain the proof, so I'm not going to show it to you. And so for hundreds of years after that, people are trying to figure out this simple, great proof that Fermat had. Now, it turns out, and I don't want to go through all the details here, but it turns out, so you only need to consider, or let's say only, need to consider the equations x to the p plus y to the p equals z to the p, if you can show where p is prime. So if you can show that there's no prime number greater than 2 for which there are integer solutions here, then that solves the general case, right? So there's the first sort of reduction. Now, so let's see here, yeah. All right, so mathematicians are have been searching for solutions. Now there was sort of incremental progress on this. The first 1770. Oh, and by the way, when was this? I want to say it was. When did he do this? I want to say, and let me just look here real quick because I have it on my computer. 1637 is when he first said this. Okay, so his claim. Sorry, let me get my history a little bit better here. So this claim was made in 1637. Oh, 1637. Now, in 1770, it was Euler prove that this is true when n equals 3. Maybe I should say p equals 3. Right, so Euler shows that there are no integer solutions when p equals 3. 1825. Dirichlet. Dirichlet and Legendre they showed that there are no integer solutions when p equals 5. The next progress, 1839. Lamé proved it for p equals 7. All right, so very slow progress, as you can see, right? I mean, we've got p equals 3, p equals 5, p equals 7, and that took, well, how long was that? You know, a couple hundred years, right, after Fermat first stated it. Now, a little while longer, so in 1847, right, so we've made this very slow incremental progress. Suddenly in 1847, the same guy, Lamé, claims that he's proved the general case, right? So Lamé claims, or let's say announces, the general proof. All right, so he says, guess what? All right, I got p equals 7, and then 8 years later, I have now proved the general case. I have proved that for no prime p, there are no, for any prime p, there are no integer solutions. No integer solutions exist. Now, here's the idea behind his proof, right? As we all know, his proof was wrong. And so I want to sort of indicate where the gap arises. So here's the idea behind his, and I got to put it in quotes, the idea behind his proof. So it goes like this. If alpha in Q is algebraic, remember an algebraic number is one that is the root of some polynomial with rational coefficients. So if alpha in Q is algebraic, then we can define, let's say algebraic of degree n, which means it's the root of a degree n polynomial. So if alpha is algebraic of degree n, then you can define Q parentheses alpha. It's the set of all things in the form a0 plus a1 alpha plus dot 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 plus a sub n minus 1 alpha to the n minus 1, where all the ai's are rational numbers. And it turns out that this is a field. If you're going on to Math 483/560, we'll be talking about these fields fairly often. And notice what this is. You can take all polynomials that have rational coefficients, and then all it is just the evaluation, right? It's been evaluated at this number alpha. So if you have, oh, and that should not be a Q. Sorry, one typo here. This should be a complex number. So if alpha is a complex number that is the root of a rational polynomial, then you say it's an algebraic number. And so evaluate at alpha, you get this thing, it's a field. And then you can consider Z bracket alpha. That's going to be the set of all things in the finite form. Do I care about the letter? Let's just use A's again. A0 plus A1 alpha plus dot 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 plus A sub n minus 1 alpha to the n minus 1, where now the ai's live in Z. All right, so just replace the rational coefficients with integer coefficients, and you get this thing denoted Z bracket alpha, and it turns out, so Z bracket alpha is a subring of Q parentheses alpha. So this gives a way to compute or to create a bunch of subrings. Actually, that was kind of a weird thing to say. It gives us a way to create a bunch of sort of interesting rings, right? These, I guess you could consider sub-rings of the complex numbers. Now, note, what we've been working with, these z bracket square root of n's, these are just special cases of the z bracket alpha. So it's just a special case. Now, here was the idea behind his proof now that we have this set up. So, Lemay, what he did, Lemay factored x to the p plus y to the p. And you could factor it this way, so it's x plus y times x plus y, x plus alpha y times dot 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 down to x plus alpha to the p minus 1 times y. So he factored this, and so this factorization is happening in z bracket alpha, where alpha was a certain root of unity, right? E to the 2 pi I over p. Okay. So his proof centered on one of the key ideas was this factorization of x to the p plus y to the p. And then he goes on with his proof, but in his proof, I gotta keep saying proof with quotes. So in his proof, it was essential that this factorization is unique. So in his proof, it was assumed that this factorization was unique. In other words, in order for his proof to work, he needed z bracket alpha to be a UFD. But it turns out, and so it was shown that this is not true. And this was due to Kummer in 1844. They didn't have the internet back then. Information traveled a lot more slowly. And so notice, Lemay announced this in 1847, right? Kummer actually proved this in 1844. Obviously, Lemay was not aware of the fact that factorization is not necessarily unique in z bracket alpha. So that once that happened, then of course the proof falls apart, and oh, in fact, it was Gauss. No, I guess not just Gauss. So anyways, this is where this z bracket root n came from, right? So just a special case of z bracket alpha. Now, just a couple more facts here. So it turns out that if n is negative and square free, then z bracket root n is a UFD if and only if n equals -1 or -2. So all other choices of negative numbers right here, right, square free, give us non-UFDs. Right, so for example, z bracket square root of minus 3, z bracket square root of minus 5, and so on, all non-UFDs. Oh, now, yeah, two more facts that I want to give you. So first of all, Kozlov in 1949. Remember, we were asking, or we know this fact right here. So we know that Euclidean domain implies principal ideal domain. And then I said, but it turns out that the reverse is not true. There exist principal ideal domains that are not Euclidean domains, right? But this is hard to show. And so it was Kozlov who actually proved this. So what did he do? He showed that z bracket 1 plus square root of minus 19 divided by 2 is a PID that is not a Euclidean domain. Okay, so now we know that the converse of that is false. And then one last thing. So Fermat's last theorem was eventually proved. And the proof was by Andrew Wiles. Now, what happened was it was in 1993 where he announced the proof, and guess what? There was a mistake. There was a gap. And it took a couple more years before he actually filled that gap, and it required a little bit of help from somebody else. What was this? 358 years later, is when he finally, when Fermat's last theorem was finally proved. Well, okay, that's it. I just wanted to give you a quick little history lesson. You have just about almost survived Math 482. All that's left, so we're going to review tomorrow. That would be on Friday. We'll do a review session, and then on I don't even know when your exam is. Next week sometime. So you still got a final to go, but you've survived. You've survived virtual Math 482 lecture. So, all right, we'll see you.